Yeah. So a person climbing up a flight of stairs, what is the sign of work done by normal force? Rishi, you said positive in the last class. Okay. Use of any answer?
So positive.
Positive. Fine. Let's see. You like the ones who gave the answer as positive, you all said it is positive because normal force on the person would be acting in the upward direction whenever whenever the person steps on the stair or places his or her foot on the stair, the normal force acts this way. Okay, wait, some other students have joined. We'll ask them also for an answer and then continue. Yeah, so just a second. They joined, but I don't see their names in the list. Okay. Aishwarya, Saket, Pawan, are you getting my voice?
So yes, sir.
Yes. Okay, fine. So yeah, tell me your answers to this problem. Aishwarya, what do you say is the sign of work done by normal force as the person climbs up?
Sir, I think it's positive.
Positive, and reason? Whenever the person's foot is on the step, the normal force would act this way, and we know the person as a whole is moving in this direction. Okay, so are you saying it is positive because the angle between normal force and displacement is acute?
So yes.
Okay. Saket, any answer?
Positive, sir.
Positive. Pawan, what is your answer?
The same positive.
Okay. The correct answer is 0. One of you tell me the basic formula for work.
Sir, F dot ds.
Integral f dot ds. Correct. F is of course the force work done by which you want to find out. Can one of you tell me what exactly is ds? I want the exact answer.
Small displacement.
Whose small displacement?
Of the object of which the force is acting on.
No. That's why I said I want the exact answer. Can any of you tell me what exactly is ds? We had discussed. Okay. ds should be the displacement of which point? Or which
Point
part?
of the application of force.
Correct. Okay. Displacement of point on which the force F is acting. Okay. Now imagine the person climbing up the stairs. Where exactly does the normal force act on the person? Where exactly does normal force act on the person?
On his foot, sir.
On the foot. Okay. When does normal force act on any foot? When that foot is placed on the step. Okay. Or do you think normal force will act on the foot when it is in air also? Does that happen?
No, sir.
No, definitely not. The foot has to be on the step. Only then normal force acts on it. Okay. Imagine the boy climbing the stairs, or imagine yourself climbing stairs. The foot that is on the step, while it is experiencing normal force from the step, does it move? Suppose your right foot is on a step. Okay. As long as it is on that step, does it move?
No, sir.
No. The rest of the body will move. Okay. But the foot which is on the step will not move. When you put the next step, when you put the other foot on the next step, then you will remove this foot from this step. Right? So, like in this diagram, if you see, the right foot of the boy is on step 1. When will the boy take off the foot from that step? When the left foot is kept on step 2, the right foot will lose contact with step 1, and then it will go to step 3. Like that. That is how we climb stairs, right? So, normal force acts on the foot. But when the foot is experiencing normal force, it is not moving. Rest of the body is moving. The exact point where normal force is acting is not moving. That is why, okay, the work done in this case is 0. Not because normal is perpendicular to displacement, not because normal force is 0. The reason is that the displacement is 0. Okay, think carefully. When normal force is acting on the foot is not moving. When it is off the step, I mean, when you lift your foot off the step, you move it forward. Okay, but that time normal force won't be acting, no? Normal force acts when the foot is on the step, and that time the foot is not moving. Are you all convinced with this or not? Pawan, did you understand?
Yes, sir.
Yusuf, did you understand?
Yes, sir.
Okay. So see, you have to think in that much detail. Fine. It seems very easy to say that person is moving up, normal force is acting upward, work done should be positive. That is wrong. Normal force is not doing any work there. If normal force had been doing work, it means normal force would have been supplying energy to you. But that is meaningless. Now, when you climb stairs, you will lose your own energy. Where do you get energy from the steps? You don't. Okay. So the work done by normal force when someone is climbing steps without slipping. Okay, we don't even have to talk about slipping. The work done by normal force is 0. Okay. Because normal force acts on the foot of the person. And when normal force acts on the foot of the person, the foot does not move. When the foot is moving, normal force does not act. Okay. So work done by normal force there is 0. Now this question, we know friction is needed for a runner to gain speed while running. As the runner gains speed in the forward direction, is the work done by friction on the runner positive, negative, or 0? Aishwarya, what is your answer?
So positive.
Why? Okay, think about it. Think about the reason. Pawan, what is your answer?
Sir, నెగిటివ్ అనుకుంటున్నాను.
Okay, can you justify?
సార్ అంటే ఫ్రిక్షన్ ఆపోజిట్ లాగుతుంది కాబట్టి
Friction acts opposite to what, sir?
సార్ మనం ఫ్రంట్ మూవ్ అవుతున్నామంటే ఫ్రిక్షన్ వల్లే కదా సార్, అంటే ఫ్రిక్షన్ బ్యాక్వర్డ్ యాక్ట్ అవుతుంది.
Friction, if friction is acting backward, what is making you go forward? We discussed this in laws of motion itself. When you are starting to walk or when you are gaining speed, your foot will have a tendency to slide backward. Friction will act forward. That is why you start moving forward. That is how you gain speed forward. Okay, keep revising the basics. So now I think you will change the answer to positive. Let it be. Rishi, what do you think?
Sir, even I had written negative. I understand.
So now you want to change it to
Yeah.
positive.
Yes.
Okay. Vanilla, any answer?
Positive only.
Saket,
Positive, sir.
Yusuf,
Positive.
answer is again 0. Why is it 0? Let's see. The runner is gaining speed. How do we gain speed? We try to drag our foot in the backward direction. So tendency to slide will be backward. Friction will act forward. Definitely friction is needed to gain speed. Friction acts forward. The runner moves forward. So velocity is in the forward direction. But again, just like the previous case, you all tell me, where does friction act on the runner? At which point? At
On his
which?
foot.
On the foot only, no? Friction will act. Okay. When does friction act on the foot? When it is in contact with the ground or when it is in air? Friction acts on
When
the
it's in contact with the ground.
obviously when it is in contact with the ground itself. Okay, now I am not able to okay, this is the right foot only, no? The person's right foot is on the ground, left foot has been taken off the ground already. Okay, so what he will effectively be doing is trying to drag his right foot in the backward direction, but friction won't allow it to go back. Friction will keep the right foot there itself. The person's left foot will move forward. Okay, that is what happens, when we walk also. Imagine, like, consider my fingers as the legs. Okay, so when one foot is on the ground, the other foot will be off the ground. The rest of the body will be moving forward, but this foot which is on the ground stays on the ground. Okay, that is how we walk. Then the next foot will be ahead, forward. Then that foot will stay on the ground. This will lose contact and move forward. But as this movement is happening, the other foot stays there itself. It doesn't get displaced. Okay, as you put one foot forward, the other foot stays on the ground at the same place. And that is the foot on which friction is acting. Yes or no? When you are, let's say, like, assume this is the right foot. When the right foot is being taken forward, the left foot stays on the ground, and that's the foot on which friction is acting. But that foot is not getting displaced when friction is acting. That is why the work done by friction in this case is also 0 itself. Okay, so this is what happens effectively. There is friction acting, but there's no displacement at this point. Friction is acting at this point only. So did you all understand any doubt in this? Okay, answer in this case is also 0. And clearly I have mentioned that assume the runner is not slipping. If there's no slipping, work done by friction is 0. Okay. Fine, let's continue the chapter. So last class we had discussed work kinetic energy theorem, which basically gave us another way to find out work done by some forces or all forces, right? I had given you one worksheet on spring force. Let's find out, or let's consider spring force now. Do any of you remember the expression for spring force?
KX.
Okay, the magnitude is kx, correct? What does k stand for and what does x stand for?
Spring constant and elongation or compression. Length of elongation or compression.
Correct. K is the spring constant and x is the elongation or compression in the spring. Fine. Just a moment. So consider a spring like this. Basically, what happens is a spring, like most solids, wants to maintain its shape. Fine. So when you leave a spring freely like this, the length that it assumes is called the natural length. Okay, I'll not explain in much detail. It's all there in that worksheet. And this is like the, like as the name itself says, natural length. So the spring is not under any kind of stress or anything, and it won't do anything if it is in this position. Okay, if it is in its relaxed length. Now you know that to compress a spring, you need to exert a force. Okay, you need to exert a force to compress a spring means the spring is exerting a force when you are compressing it. Okay, that is why you need to exert a force. The spring offers resistance. It doesn't allow you to compress it. But if you want to do that, you will have to exert a force. So if the spring is compressed, let's say it is compressed by a distance x. Okay. Like from everyday experience, you must be knowing to compress a spring more and more, you will need to exert more and more force. Small force will compress it only a little bit. Larger amount of force will compress it more. That means the force exerted by the spring depends on how much it is compressed. And it is proportional to how much it is compressed. Similarly, to stretch a spring also, you need to exert a force on it. To elongate a spring. That means when a spring is elongated, let's say by a distance x, it will be exerting a force in the backward direction now. Towards itself, it will be pulling. And that force by which it pulls is also proportional to x, how much it is stretched. Okay, so basically if you compress a spring, it will push. If you elongate a spring, it will pull. And by what force, by what amount of force it pushes or pulls depends on how much it is compressed or elongated. The formula for spring force is F is equal to Kx, where x is of course the elongation or compression, and K, obviously it's the proportionality constant between force and the elongation or compression. Elongation or compression, I'll call it as deformation. Okay, the force exerted by a spring is proportional to deformation in the spring. It could be either way. And K is called as the spring constant. Basically, it's nothing but the stiffness of the spring. Suppose there's one spring which can easily be compressed or elongated, then it will have a small K value. Let's say there is another very thick spring which is difficult to compress or elongate, then it will have a large K value. Okay, that is what is spring constant. You can say K is equal to F by X. Basically, spring constant is the force required to cause a unit deformation in the spring. To compress the spring by 1 centimeter, how much force is needed? Or by 1 meter, how much force is needed? That is what is spring constant. So if you need a lot of force to compress it just by 1 unit, then spring constant will be high. If you need only a little bit of force to compress it by 1 unit, spring constant will be low. So spring constant is a measure of stiffness of the spring. Okay. Let's solve some problems based on this. So remember that spring force, the force exerted by a spring, depends on the extent by which it is deformed. So consider a situation like this. Just a moment. Let's say a block is connected to the spring and the spring is compressed. Okay, in this present state, it is already compressed. Assume this is the natural length of the spring and it is compressed already by, say, some 20 centimeters. Let's assume the spring constant to be 200 force per unit length, so Newton per meter. Assume the mass of the block is 2 kg. Smooth surface. What will happen if we release this block? The spring is already compressed, as I said. If you release the block, what is going to happen? What does a compressed spring do? Push or pull or nothing?
Push, sir.
It pushes. So the spring will exert a force on the block this way. As a result, the block will start moving forward. Okay. And till the spring returns to its natural length, it will keep on pushing. Okay. So throughout the journey or throughout the displacement, the spring will exert a force on the block. But initially it is compressed by 20 centimeters. But as the spring relaxes, that compression will decrease. Okay. Like after some time, after a short interval, the block will come to this position. Then the compression of the spring won't be 20 centimeters. It may be only 15. When the block comes to this position, the spring's compression may reduce to 10. If the compression in the spring is changing, the force exerted by the spring will also change. And compression is decreasing, so the force will also decrease. So we can properly indicate the force with an arrow which is becoming shorter and shorter. This is the force that the block experiences. Okay. But it will keep being pushed. I mean, the spring will keep pushing the block till it goes to the natural length. Okay. Surface is smooth, so the block will have to slide under the influence of the spring force. Suppose it reached the natural length. Okay, spring has, okay, just a moment, I'll take another diagram. Let's say the spring has returned to its relaxed length. What will be the state of the block at that instant? Will it be at rest or will it still be moving forward? The spring has returned to its natural state, relaxed state. Earlier it was compressed. By pushing the block forward, it came to its natural length. Will the block immediately stop or will it go to the other side?
It will stop, sir.
Can you justify that? It was being pushed, right? If it was being pushed, it would have gained some velocity. Where will that velocity go then?
Sir, but the force will become 0.
Let force become 0. But till then it got velocity. How will the velocity disappear?
Sir, I think the spring will pull the block.
When will spring pull the block? Generally, when will a spring pull?
When it becomes elongated.
But it didn't become elongated. It just came to its natural length, right?
Yes,
So
sir.
So will the block have experienced a backward force? No. Others, any answers? Rishi, what do you think will happen? Will the block, like after coming to the natural length, do you think the block will stop or will it move further?
Sir, I think it'll remain at the same position because there's no force acting on it. Like, because it has come back to its normal position, there's like, since you said the natural length spring is relaxed, right? So
Spring is
it
relaxed,
shouldn't.
spring is not exerting any force. But from this position, okay, let's call the initial position as A, this natural length position as B. As the block moved from A to B, it was pushed by the spring. It would have gained some momentum, it would have gained some velocity. Where will that velocity go? What backward
Oh yeah,
force?
it'll move slightly, sir. It moves slightly in from B, like towards the right.
It will cross that position.
Yeah.
Okay, that is correct. When the block comes to, or when the spring comes to the natural length, okay, or when the block comes to this position, it will have some velocity, because till then it was being pushed. At that point, it's not experiencing any force. That's okay. If force is not there, acceleration won't be there. Why will velocity not be there? It gained velocity, it will have that velocity. And with that velocity, it will cross that position also. Once it crosses that position, the spring will start pulling it back. Okay, because once the block crosses that position, the spring is now stretched. The force will start acting in the backward direction. The block is moving forward, but force is acting backward, so its velocity will reduce. And it will reduce further and stop somewhere. And then it will come back. It will keep oscillating back and forth. Have you seen spring toys oscillating or not?
Yes, sir.
Any toy made of spring, have you seen it oscillate or not? There are keychains, bobblehead keychains, they oscillate. What other systems? Sometimes on a swing also, the chair of a swing, sometimes it has like the chain has a spring in it, so it will oscillate. So usually from a compressed state or an elongated state, when a spring comes to its natural length, it won't stop there. It will go to the other side, because by the time it comes to natural length, the object would have gained some momentum. And with that momentum, it will cross and move to the other side as well. We'll discuss this in detail. If there are other forces at play, then it may stop. It may not continue oscillating. It may just oscillate once or twice and stop. Lots of things can happen. Okay. But did you all understand why the block will not stop at the natural length, but cross and move to the other side? Any doubt in this? Okay. So let's solve one problem based on this. Remember the expression for spring force, it is Kx. Magnitude is Kx, direction you have to decide, okay, based on the problem. So spring was initially compressed by 20 centimeters and the block is released from rest. Initial velocity of the block is 0. So you know the block is going to move forward, the spring will relax. First thing I want you all to calculate is work done by the spring force as the spring returns to its natural length. Okay. Let us discuss this and solve. One of you tell me, as the spring returns to its natural length, the force that it exerts is constant or variable?
Variable, sir.
The force which the spring exerts on the block is a variable force. Correct. And you are asked to calculate work done by that force. Can one of you tell me what is the formula for work done by a variable force? Vanilla, don't answer. Someone else.
Sir, integration of
Sir,
F dot ds.
Correct. Since the force is variable, it is integral F dot ds that we have to use. Okay. Now it's a rigid block. I told you, no, in solid objects which are not rotating, all particles will undergo the same displacement. Now the spring is connected to the block at only one point, but the displacement of that point is same as the displacement of the entire block. Now in that person running or person climbing stairs case, person is not a rigid body. Okay. Like our knees, the knee joint rotates. Fine. Our elbows rotate, elbow joint rotates. Our hip joints rotate. Okay. So person is an example of a system in which different particles can move with different velocities. Like now I'm moving my hand, but my head is not moving. Okay. So human body is not a rigid object. So in that case, overall displacement and a particular point's displacement need not be same. But in this case, this is a rigid block that we are considering solid object. Okay. All points will undergo the same displacement. Rotation is not happening. Fine. So we need to use integral F dot ds. We know the expression for the force. We still need an expression for displacement and the angle between force and displacement. All these things are required. Let us think carefully. Follow me, all of you. The force expression is kx, where what is x in this? In the expression for spring force, what does x mean?
Like from the natural length.
Deformation. Okay. Compression or elongation from the natural length. Fine. So you can see the natural length that is indicated here. As this block is moving, as this block is getting displaced, at a random instant, you assume the block is somewhere here. The spring is in the process of relaxing. Okay. It will still be exerting a force. The force will be acting like this. Let it be. But remember, this is x. Okay, the compression in the spring is what you call as x, and the force depends on that. Let it be. We know the magnitude of the force, it is kx. Fine. Next, you have to express displacement, ds. You can't simply integrate kx ds because x is a variable, then you have to integrate with respect to that variable only. So you'll have to express the displacement ds in terms of dx. Okay. Imagine the block moving forward a little bit, maybe from here to here. Let this be the displacement ds. Then the next value of x at the new position, x will be this much. Now tell me, is the displacement ds equal to the change in the value of x or not?
Yes, sir.
Do you all agree with this? During a small displacement ds, is ds equal to dx, the change in x, or not? Pawan, what do you say?
Sir, negative indication.
Yeah, negative sign we'll see, but magnitude wise, are they the same or not?
Yes, sir, equal.
Okay. Aishwarya, do you agree with that or not? Magnitude of ds is same as the change in x.
So yes, sir.
It will be. Okay. So magnitude wise, ds is equal to ds. Ds is equal to dx. Okay. Sign, negative sign and all we'll include later. Next, we have to take the dot product between force and displacement. So it is going to be F ds cos theta. Force is to the right because spring is compressed, it will push. Block is also moving to the right only. Then angle between force and displacement ds, the angle theta is 0. Fine. Therefore, work done by the spring force, which is basically F dot ds, which we are writing as F ds cos theta, can now be expressed as kx dx cos 0. Cos 0 is 1. Okay, so you have to integrate kx dx, where again you have to remember that x is the compression or elongation in the spring. Now, by what extent was the spring compressed initially? 20 centimeters. So x value initially is 20. If you convert it to SI units, it is 0.2 meters. We want the answer for work in SI units. So everything has to be considered in SI units. And till when do you want to find out the work done? Till the spring returns to its natural length. When spring returns to natural length, the compression or elongation becomes 0. So the limits will be from 0.2 to 0. And K value is given in the problem as 200. Mass is not necessary anyway. Yeah. So K is a constant, put it outside the integral. So work done becomes K is 200. Can one of you tell me how much is integral x dx?
X square by 2, sir. X
Square by 2. That by 2 and this 200 will become 100. You will be left with x square 0.2 to 0. Substitute limits. Substituting upper limit makes it 0. Substitute the lower limit. 0.2 whole square is 0.04. So the answer turns out to be minus 4 joules. But minus doesn't make sense here. Force and displacement were in the same direction. Why did we get a minus sign? Exactly what Pawan was saying. We have to include a negative sign here. ds is negative of dx. Okay, why? Because when ds is positive, observe this carefully, all of you. Students tend to make mistakes. Of course, if you get a minus sign, you know whether the final answer has to be positive or negative. Force and displacement are in same direction. Answer has to be positive. You can simply ignore the minus sign. But mathematically also, your steps have to be correct. Okay? So suppose the way we visualize the object to be moving, let's say ds is positive. Okay. Initial value of x, let's say at some position, the value of x is 10 centimeters. And the small displacement is some 0.2 centimeters. Just a random value that I'm taking. If ds is 0.2, what will be the next value of x? How much is the remaining compression? 9.8. Okay. At one instant, the compression was 10. The spring relaxed by 0.2. That means the compression will still be 9.8. Then what is the change in x? Final minus initial, that is minus 0.2. So when ds is 0.2, dx is minus 0.2. They are negatives of each other. That's why we have to include a minus sign. And that minus sign will make the answer positive. Okay. So the work done by the spring during this displacement of the block is 4 joules. That much energy will be given to the block. Is this clear to all of you? Okay. If you have any doubts, you can ask. Spring was initially compressed. As it relaxes and comes to natural length, you are asked to find out how much work will be done by the spring force. We first recollected the expression for spring force, F is equal to kx, and we concluded that it's a variable force. Obviously, as the spring relaxes, the compression changes. It's a variable force. So we decided to use the formula for work done by variable force. Fine. We know the expression for spring force, kx, that's okay. Displacement is where you need to be careful. In the expression for spring force, x is not a displacement. X is the compression of the spring. You have to express the displacement in terms of compression of the spring. That was the tricky part in this solution. ds is equal to minus dx. Then you integrate, you'll get the answer with proper limits. Okay. Now you all tell me, as the block moves from this position A to the relaxed position B, during that journey, what all forces acted on it or would have acted on it?
Spring force, normal and weight, sir.
Normal, weight, and spring force. Weight will definitely be acting. Normal force will definitely be acting. Spring force is acting, we know that. Okay. Displacement you can see is to the right. Every point of the object is moving to the right only. So how much is the work done by weight in this displacement? How much is the work done by normal force during this displacement? How much are the work done by weight and normal force during this displacement?
0, sir.
We'll see. Yusuf, you tell me, in which direction is weight acting?
Down.
Down. In which direction is the object getting displaced?
So right side.
Right side. What is the angle between force and displacement?
90.
So work done should be? When force is perpendicular to displacement, the work done will be 0. Is it clear? Because work done is F dot S, which is F S cos theta. Theta, the angle between weight and displacement is 90 degrees. Cos 90 is 0. That makes the work done by weight 0 in this case. Okay. Saket, tell me, how much will the work done by normal force during this displacement be?
0, sir.
0 for the same reason. Normal force, displacement perpendicular to each other. That means spring force is the only force doing work on the block. If spring force is the only force doing work on it, then the work done by spring force itself will be the total work done on it. And one of you tell me the statement for work kinetic energy theorem. Vanilla, don't answer. Anyone else?
Half mv square minus half mv square.
Left hand side. Tell the complete statement.
Change in kinetic energy is equal to half mv square
And a
minus.
change in kinetic energy, half mv square minus u square. Even small children will tell. What is work energy theorem? You didn't talk about work at all.
Oh, it's the total work done by all the forces.
Total work done by all forces is the change in kinetic energy. Now in this problem, we have concluded that spring force is the only force doing work. So this 4 joules itself will be the total work done on it by all forces as it comes to the natural length. Then this should be equal to the change in kinetic energy of the block. It will be, okay? Therefore, you can write 4 is equal to half. Mass of the block was 2 kg. V square minus, the block was released from rest. It was given to you in the problem. The initial velocity of the block was 0. Okay. So cancelling these, you get V square is equal to 4. That means V is equal to 2 meters per second. What V is this? The speed that we were talking about. When the block or when the spring returns to its natural length, the block will be in this position. It was pushed till then. So it would have gained some velocity by the time it reaches there. That velocity is what we now found as 2 meters per second. Okay, so by calculating work, we are telling what is the final velocity of the object. You could have answered it by calculating acceleration. You know spring force, no? Divide by mass, you will get acceleration. Variable acceleration, use those integral formulas. You can find out velocity that way also. But we use the work kinetic energy theorem. Is this clear to all of you? Will you be able to solve if I give you another question like this? Tell something, yes or no?
Yes, sir.
Others?
Yes, sir.
Okay, let's see. Try another question. Okay, smooth surface itself. In the meantime, you recollect what we did in the last question, okay? Assume the mass of the block is 4 kg. Spring constant this time is only 100 Newton per meter. Spring is initially elongated. Okay, let's say the block was already in the process of coming back. So the block has a velocity let's say 1 meter per second already. And the spring is still stretched by 20 centimeters. Or, okay. Fine, let it still be stretched by 20 centimeters. So block is moving to the left. Spring is also in the process of relaxing. But it's still not relaxed. It's still stretched, as you can see. So it will be pulling the block. Block speed will further change. Now, this time I want you all to calculate speed of the block when elongation of the spring becomes 10 centimeters. So not when it comes to the natural length. Before coming to natural length itself, some instant the elongation would be 10 centimeters, right? At that moment, I want you all to find out the speed of the block. Do this, all of you. Initially means the moment when we started observing this system, the spring was stretched by 20 centimeters. So basically what we want is the speed of the block when it comes here to an elongation of 10 centimeters. I got one answer as under root 7 by 2. We'll see. Another answer 1.32. I don't give decimals and all. Like before simplification, what is the answer you got? Fine. Let us discuss. Saket, how are you trying to solve this?
Sir, I started by the same method as above, and somewhere in that process I messed up and I could not do anything.
Okay. What is the method you are trying to use? Work energy theorem.
Yes, sir.
Okay. So the first thing we have to do is calculate work done by the spring force, equate it to change in kinetic energy of the block. Right. Just a moment. There. Right. Now, see the block is moving to the left. The spring is in a stretched state, so it will be pulling. So the force on the block is also to the left itself. Force displacement are in the same direction. Work done should be positive. Kinetic energy should increase. Speed must be more than 1. Okay, we'll see. Spring force is a variable force. So integral F dot ds. Same ideas that we applied in the last case. We can write it as kx dx with a minus sign. Okay. And limits for x this time, initial elongation of the spring is 20 centimeters. So the initial limit, lower limit will be 0.2. Finally, where we want to find out the speed of the block, the elongation in the spring is only 10 centimeters. So final upper limit will be 0.1 meter. 10 centimeters is 0.1 meter. That's all. K is 100. So you have to be careful with the calculation. Integral x dx is x square by 2. 2 and 100 cancel. You'll be left with 50. 0.2 and 0.1. Substitute limits now. 0.1 whole square is 0.01. 0.2 whole square is 0.04. Effectively, it becomes minus 0.03. Minus minus cancel. 50 into 0.03. That is 0.3 into 5, 1.5 joules is the work done. Right. And as the block moves to the left, there are 3 forces acting on it: spring force, its weight, and normal force. And for the same reasons as we discussed before, weight and normal force won't be doing any work. Then the work done by the spring force itself is the total work done. Therefore, this 1.5 joules can be equated to the change in kinetic energy of the block. Mass of the block this time is 4 kg. And v square, that is the final speed squared, minus u square is the initial speed squared. Initial speed is 1 meter per second. That was given to you in the problem. 1.5 is 3 by 2. Send the 2 this side. It becomes 3 by 4 is equal to v square minus 1. That means v square is 3 by 4 plus 1, 7 by 4. So v becomes whole under root 7 by 4, or simply root 7 by 2. Okay. Pawan, is this what you got? Is this what you told as 1.32?
Yes, sir.
Okay, correct. Saket, where did you lose your way?
So, very first step, sir.
Limits you substituted wrong.
Yes, sir. I also did not take the minus sign.
Minus anyway, doesn't matter. You may get a negative answer, but you know work done is going to be positive here because force at displacement were in the same direction. So you can ignore the minus in your answer. But that
Limits.
visualization should be done. Okay.
Yes. Limits also I took wrong, sir.
Okay. Okay. Spring force is tricky only, you need to be careful, especially work done by spring force. But in this chapter itself, we'll discuss some other techniques which will help us easily solve these problems. I'm intentionally making you solve these problems the difficult way. Later, you'll learn another method where you can answer this directly. Okay. Fine. So that way you can calculate work done by spring force, which is one of the variable forces that we come across. Okay, work energy theorem is done. Work done by spring force is done. Fine. Now, basically in nature, see, there are a lot of forces. Okay, like tension, normal force, spring force, friction, gravity, weight. Okay, you can come up with many different names for forces. But fundamentally, there are four forces in nature: gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. Now, weight is gravitational in nature, tension, normal force, these are all electromagnetic in nature. Okay. How much tension a string exerts depends on the force of attraction between its molecules. Okay. That is all electromagnetic in nature. Okay. Nuclear force we won't discuss as of now. Okay. So those are the four fundamental forces in nature: gravitational, electromagnetic, strong nuclear, weak nuclear. Okay. Now, all the forces that we come across can be classified into two types: conservative and non-conservative forces. Can any of you explain the meaning of this word conservative? General English meaning. Meaning of the word conservative. Okay. Anyway, Google gave me this meaning. Averse to change. Averse means against. Okay. So not willing to change. That is what is conservative. So basically they keep something preserved as it is. They don't allow something to change. Okay. So basically conservative forces keep something constant. Now what that something is also we'll discuss, but there's something they keep constant. That's why they are called conservative. Non-conservative forces, on the other hand, make that thing vary. They are called non-conservative. And the thing we are talking about is something called mechanical energy. But we first need to talk about conservative, non-conservative forces. Then we can talk about mechanical energy. Now there's a definition for this. Conservative forces are forces the work done by which does not depend on the path followed by the object. Okay. Work done must never depend on the actual path followed by the object. See, work done involves a displacement, right? So work done during a particular displacement should not depend on how the object actually moved. It should only depend on from where to where it has gone. Okay. So work done must never depend on the actual path followed, but only depend on initial and final positions. Only depending on initial and final position means only depending on displacement. So actual path does not matter. Displacement is what matters. Such forces are called conservative forces. On the other hand, non-conservative forces. Work done varies depending on the actual path followed. What does that mean? For the same displacement means same initial and final positions. If you go along one path, you get one amount of work done after doing the calculations. Okay. If you go along some other path, you get a different amount of work done when you do the calculation. Such forces are called non-conservative forces. Okay. So if you want to decide whether a force is conservative or non-conservative, you will have to choose a random path, find out the work done, and prove that the work done depends on initial and final positions, not on the actual path chosen. If you are able to prove that, it is conservative. If you find that you are not able to prove that, then it is non-conservative. So whether a force is conservative or not depends on the work done by it along different paths. Okay, based on that, you will be able to judge whether it is conservative or not. Let's consider an example. Example of what? You will only tell. Let's consider a constant force. Can one of you tell me the formula for work done by a constant force?
F dot S, sir.
F dot S. Integral F dot ds changes to F dot S. Force dot displacement. Now force is constant, okay. Displacement by definition depends only on initial and final positions. No, the path does not matter for displacement. Displacement is final position minus initial position. It only depends on the final and initial positions. So now you all tell me, work done by a constant force, does it depend on the path or does it only depend on initial and final positions? Aishwarya, what do you think?
It depends on initial and final position.
That's all. Okay. It depends on the the formula itself is telling you that it depends on the overall displacement. The force is not variable, no. So force does not depend on where the object is going and all. Force is fixed. Displacement only depends on initial final position. So the work also depends only on initial and final positions. Therefore, okay, let us complete this statement. Depends only on initial position and final position, not on the actual path. I mean, it does not depend on the actual path. So tell me now, a constant force is a conservative force or a non-conservative force?
Conservative force, sir.
Automatically, by definition, it becomes a conservative force. Therefore, a force which always remains constant can be called conservative. Not can be called, it is conservative in nature. What it conserves is mechanical energy. We'll talk about that later. But constant forces are conservative forces. Now see, we had discussed many forces till now: tension, normal force, friction, spring force, weight. Out of all these, which is one force that always remains constant, irrespective of what is happening to the system?
Weight, sir.
Weight. Okay. Weight of an object, we just write it as mg, but I'll have to put a star here. M is the mass of the object. Mass of an object may not change. Acceleration due to gravity, no, it will actually change when you go too far away from the earth. But as of now, even in the next chapter, we'll assume acceleration due to gravity is constant, uniform, because we are only discussing about small distances above the earth. Throwing a ball to 40 meters, throwing a ball to 80 meters, object dropped from 100 meters. these distances are nothing compared to the size of the earth. Okay, even the altitude at which aeroplanes fly, how high do aeroplanes go roughly? Let me ask Google. How high do aeroplanes fly in kilometers? And the answer is most commercial passenger flights, passenger jets, fly at an altitude of 8 to 11 kilometers above the surface of Earth. So, what is the radius of Earth, anyone? Earth is a huge sphere, almost, okay? And its radius is close to 6,400 kilometers. That is how big the Earth is. And compared to that, a height of 8 to 11 kilometers is negligible. Okay, so within that height also, gravity won't change significantly. So we'll assume the weight of an object is constant for all the displacements that we will be considering for now. So from now onwards, we are going to treat weight W is equal to mg as a conservative force. Okay, so out of the forces that we have discussed till now, weight is one of the conservative forces because it's a constant force, and we need not prove that work done by it will be same in all paths. Work done by a constant force is F dot S. So irrespective of path taken, it only depends on total displacement, initial position to final position. Okay, so weight is a conservative force. Fine. Because it's a constant force, it became conservative. It doesn't, I don't mean to say that non-constant forces are non-conservative forces. There is a chance of them also being conservative. Okay, but constant forces are definitely conservative forces, that much we can say. Okay. Let us consider another example. Friction. Okay. Assume there is a rough horizontal surface. We want to check if friction is a conservative force or not. So what we are going to do is, we are going to take an object from one position to another position along two different paths. And we will see if the work done is same or not. If it is not same, friction is non-conservative. Okay. So that's the idea. Let's say a block is slid, say from this position. Let's consider a small block only, ignore the dimensions of the block. And just because I'm saying ignore dimensions, don't ignore mass. Compared to the displacements that it is going to undergo, the size of the block is small, but it has mass. Okay, let's call this position as A. We are going to take it from A to another position B, where the distance between A and B is, let's say, 20 meters. So in one case, we will take it straight from A to B. That is case 1. In another case, we will drag it back by, let's say, 5 meters and then slide it forward till it reaches B. So along two different paths, we are taking it to the position B. We have to check if the work done along these two paths will be same or not. Okay, let's call this extra position as C. Fine. Let's consider some mass. Assume the mass of the block is 2 kg and coefficient of friction, let's say, is 0.5. Simple calculation. And the block is being dragged by horizontal forces. Vertically, we are not disturbing. So if there is no additional vertical force, can one of you tell me how much normal force will be acting on this block?
20 newtons.
Weight will be balanced by normal force. So normal force is 20 newtons. Okay. And when it is being dragged from A to B or A to C and then to B, what kind of friction acts on it? Why are others not responding? Only Vanilla is responding and sometimes Rishi responds. What kind of
Kinetic
friction? Kinetic friction. Formula is mu k into N. So 0.5 into 20. 10 Newton friction will be acting on it as it is dragged forward or backward. Fine, that's the magnitude of friction. Direction we will decide based on how it is being dragged. Okay, let's consider the first path. When it is taken directly from A to B. Tell me, as it moves from A to B, what is the direction of friction? Saket.
Yeah, towards the left side.
As it is dragged to the right, friction acts to the left, but displacement 20 meters is towards right. So Saket, tell me how to calculate work done by friction.
So Fs cos theta, like frictional force into
Frictional force, displacement, cos of angle between them. Correct. Frictional force is 10 Newton. Displacement is 20 meters. What's the angle between friction and displacement when it goes from A to B?
180.
180, so minus 1. So work done by friction as it is taken directly from A to B is 200 joules. Minus 200 joules, sorry. Okay. Now we have to see if the same amount of work will be done when it is first taken to C and then to B. Okay, let's do that part now. Pawan, tell me, when the block is taken from A to C, how much is the work done by friction? Formula is still Fs cos theta itself. How much friction acts on it?
Sir, 2.5.
What 2.5? Work done or friction?
Sir. Newton 0.5. Sir, 10. Friction 10.
Friction is 10 newtons. Okay. Displacement is how much?
5 meters.
5 meters. Angle between friction and displacement?
Sir, 180.
180. So when the block is taken from A to C, it is dragged to the left. Friction will act to the right. Okay. The angle is again 180 minus 1. So minus 50 joules is done. Okay. Next, it is taken from C to B. Aishwarya, tell me, when the block is taken from C all the way to B, how much is the total displacement?
So minus 250.
Oh, I think you told the work done. Okay, fine. I asked you for displacement, 25 meters.
25.
So second part, when it is taken from C to B, same formula for work we'll be using, Fs cos theta, because friction is constant here, constant force formula we are using. 10 Newton friction, 25 meter displacement, angle 180. So minus 250 joules. Therefore, I think it is obvious now. A to C and then C to B if you take, the total work done is minus 300 joules. Whereas if it is taken directly from A to B, the work done was only minus 200 joules. They are not same. They're not equal. And if the work done is different in different paths, despite the initial and final positions being the same, what do we call such a force? Conservative or non-conservative?
Non-conservative.
Non-conservative. Therefore, friction in general is a non-conservative force. It does not try to conserve this quantity called mechanical energy. Now, what exactly is mechanical energy? We'll learn in the next class. And next class is very important. We will define potential energy in the next class. Okay. And again, see, just like how you all answered positive for work done while climbing stairs, you will all give negative, wrong answers for potential energy. I mean, the ideas that you were taught till now will have to be modified. Okay, so don't miss any classes. Don't miss any of these discussions also. Okay. So let's quickly revise what we discussed today. We first solved those two questions, and you can like ask this to your friends also. They'll also give the wrong answer only. You can explain why it is 0. Next, we talked about basic behavior of spring force, and we solved two problems where we calculated work done by spring force. Okay, and spring force is variable. We integrated and calculated the work done. After that, we talked about a classification between a classification of forces called conservative, non-conservative. Okay? Definition is very important. Work done by a conservative force must never depend, not just in one case. You take it in any path, the work should never depend on the path. Then such a force is called a conservative force. Even if one of the paths, if along one of the paths the work is different from the other paths, the force will be called non-conservative. Okay. There is another way also to define conservative forces. Listen. Work done by, okay. Work done by a conservative force. We are saying it depends only on initial and final positions, right? This is the definition that we had already discussed. It does not depend on the path followed. Okay. Now consider two positions. Let's say this and this. Under the influence of a particular force, if the work done along any of these paths is always the same, you call it a conservative force. Okay. So whether it went straight from A to B or took a small detour or took a large detour should not matter. Now you consider 2 points which are side by side. Okay, let's say the starting point is here, the ending point is also here. Now you all tell me, if the starting point and the ending point are the same, what is the overall displacement?
Sir, 0.
0. If the final position is same as initial position, it means the total displacement is 0. Okay. Then whether you take this path to go from A to B, or you take this path to go from A to B, or you stay there itself without going anywhere, without any displacement, the work should be same. If the force is conservative, the work should be same in all these paths, and it should be the same as what it would be if the displacement is 0. And you all tell me, if an object doesn't move at all, what is the work done?
0, sir.
0. So if it is a conservative force, then the work done along any of these paths, the blue case, okay, the work done along any of these paths should be 0 itself. Why? Because if the object stayed there itself, the work done is 0, no? Then if it went around any of those paths, it is coming back to where it started from. So those paths also, work done should be 0. So this is the other way of defining conservative force. Work done by a conservative force in a round trip. Okay, round doesn't mean it has to be circular. It just means the final position is the initial position. Work done by a conservative force in a round trip is always, okay, no exceptions. It should always be 0. This is another way of defining a conservative force. Okay, but this follows from the earlier definition that work done should be independent of path. Okay, we'll stop it here for today. We'll continue on Friday. Friday, we'll discuss the idea of potential energy, and we'll also derive the formulas for potential energy in some cases. Now, from childhood, you all must have learnt one formula for potential energy, mgh. Okay, we will make some corrections to this formula. We'll learn what exactly or when exactly you can use this formula. And we'll also discuss some other formulas for potential energy. Okay, this is actually something called gravitational potential energy. Next class we'll discuss spring potential energy also. We'll prove that spring force is a conservative force, or I'll send you a worksheet tomorrow in that you will prove that spring force is a conservative force. And for every conservative force, we can define a potential energy. Now, gravitational force is conservative. We have discussed in today's class. Weight is a constant force, conservative force. Spring force is a conservative force. You will prove in the worksheet. Then we'll derive an expression for potential energy stored in a spring. Okay. Fine. Thank you all. We'll continue on Friday.